This lesson is ultimately about binomial probability distribution, but let's start with a brief review of combinations. Consider the following. How many ways can we choose 5 people from a group of 8? Well, suppose these are our 8 people. Or for simplicity, call them A, B, C, D, E, F, G, and H. I've taken the time to write out all 56 ways that you could choose 5 people from this group of 8. We call this 8 combination 5 or 8 choose 5. But writing them all out seems like a very impractical way, and it turns out we can do the same calculation on a calculator. Now, in some situations when we don't have a calculator, we can use the factorial method to calculate this. If you've never seen the factorial method, it probably looks a little strange. It's not going to be what we recommend today, but it is a possibility. Another thing that you may have seen in the past is the Pascal's triangle method. If you're not familiar with this, don't worry, this is not what we're advocating here. But for those of you who have heard of this before, you can use Pascal's triangle to find this 8 combination 5. My recommendation is to use a graphing calculator. All you need to do is find the NCR function and type 8 NCR 5, and the calculator will tell you that this is 56. The NCR function can be found by pressing the math key and hitting the left arrow will bring you to the PRB or probability menu, and among those options you'll find NCR. So how are combinations used in the binomial probability distribution? We'll consider the following situation. Suppose we have a team that wins 40% of their games. Suppose that team is going to play 8 games. How many games will they win? Well, of course, there's no way to know. They could win anywhere between none and all 8 of them. But what we could do here is we could make a table showing the probability of them winning 0 games or 1 game or 2 games using a probability binomial formula that you'll see in a minute. So just to start in the middle of the table, let's examine this question. What's the probability that they'll win exactly 5 games? In other words, how do we fill in this portion of the table? If I can teach you how to fill in this portion of the table, you'll know how to fill in the entire table, and you can answer any question about the probability of any number of wins. Well, it turns out to complete this red box, we have to do this calculation. Let me tell you where each number in this expression came from. This comes from 8 total games and 5 wins. Here's the probability of winning any individual game, raised to the power of 5 games. Here's the probability of losing any individual game. If you have a 40% chance of winning a game, you therefore have a 60% chance of losing. Raised to the 3rd power, which represents the number of losses in the scenario of 5 wins out of 8. Calculating all of this leads to about a 12% chance that this team will win exactly 5 games. But this same method of calculation that I used here can be used on the entire table. Now, I've only shown you one of these calculations, but if you modify the numbers suitably, you'll be able to calculate any line of this table, which I've done for us. And once you've completed this table, you can answer any question about any number of wins. For example, what is the probability that the team will win at least 3 games? Recall that at least 3 means 3 or more, and we soon realize that if we add up these probabilities, we will get the probability of this team winning 3 or more games. In other words, 3 through 8, or 3 through all of their games. Adding these up gives us about 68%. Let's consider the same situation with the same team who wins 40% of their games, but let's extend their season, let's say, to 50 games. So let's consider this situation. If this team is going to play 50 games, they could win anywhere from none of them to all of them. So what I've done here is I've calculated the probability of 9 wins through 31 wins. In other words, I haven't shown the entire table from 0 through 50 wins, because it seems to me that anything below 9 wins is so improbable, or anything above 31 wins is so improbable that we can neglect those portions of the table. So by choosing to express the table from 9 to 31, this is kind of an arbitrary way, or an arbitrary cutoff, where I just haven't shown the very low probabilities. Is it possible that the team will win 7 games? Is it possible that the team will win 40 games? Mathematically speaking, yes, but realistically speaking, no. So now let's consider the question, what is the chance of this team winning at least 18 games? Recall, at least 18 means 18 or more. Well, to do this, I would have to add up all these probabilities. But when the number of games is this high, the calculations become a little bit overwhelming. I mean, imagine how many calculations went into this table. Just reminding you, each one of these is a labor-intensive calculation on its own. And so, consider the following situation. If we were to graph all of the probabilities in this table, we'll notice a familiar shape. The distribution looks very much like a normal distribution. So how can we use a normal distribution to approximate the sum of 18 or more games? If we can find a suitable normal curve as shown here, then finding the sum of the probabilities in the red box would be about the same as the red shaded area under the normal curve. So let me show you how to find a suitable normal curve. First of all, in this case, the mean of the normal curve would be 20. You can get that by multiplying the 50 games times the 40% probability of winning each game, or by doing n times p more generally. But aside from this formula, this makes almost intuitive sense that this curve would peak at 20, because 20 is the most likely outcome, because 20 games is 40% of their total games. For standard deviation, the calculation is a little bit more involved, but it turns out that we can compute the standard deviation by just taking the square root of the number of games, n, times the probability of winning each game, P, times the probability of losing any given game, or 60%, also known as Q. So back to the question of 18 or more games represented by the red box. To use the red shaded area, instead, we could use 18 as a starting point. But it turns out we get a better approximation if we don't use a whole number. Now, of course, there's no such thing as winning 17.5 games, but using 17.5 in the normal distribution will better approximate what we really want to calculate, which is the sum of the bars in the red box. So back to finding the red shaded area. Recall that we'll need to find a z-score for 17.5 and then use normal CDF. Calculating a z-score gives us negative 0.72, and then using normal CDF on our calculator gives us a 76.4%. And what that means is that we've approximated the probability of this team winning 18 or more games by using a normal distribution instead of the binomial probability distribution. By the way, as a side note, I took the time to add up all the numbers in the red box, which I wouldn't even recommend making in the first place, but just for comparison's sake, those probabilities ended up to be 76.3%. So our estimate of 76.4% is quite close. That concludes the lesson.